Welcome back to Introduction to Software Reverse Engineering. Today we are going to talk about the basics of Windows programming so that you are aware of the important parts of the Windows operating system and how they affect programming for the platform. This module covers subjects such as Portable Executable file format, Windows memory model and its features, and we will pick into different Windows APIs. Let's get started. Let's talk about the foundation of Windows applications. When we build applications for Windows, we're essentially writing code that interacts with the operating system through its Application Programming Interface, or API. This usually involves using languages like C or C++ to tap into the Windows-specific functionality. The Windows API, or Win API, is the key to creating graphical user interfaces, handling user input, and accessing system resources. Understanding how the API works is crucial to reverse engineering of Windows applications, and that's what we'll be exploring in this module. Let's take a step back and look at the history of Windows. Understanding the evolution of the operating system will give us some context for the state of Windows programming. First, there is the DOS era, which dates back to the early 90s. Then we have the early versions of Windows from 1.x to 3.x, which were built on top of DOS, and quickly disappeared from the stage with the appearance of Windows 95. Next up is the Windows 9X line, which still used DOS under the hood, but added more modern features. This line of operating systems consists of Windows 95, 98, and Millennium, which was released in 2000. And finally, there is the Windows NT line, which marked a major shift toward a more robust and secure operating system in comparison to DOS and DOS-based versions. Windows NT debuted in 1993 and is still the foundation for modern versions of Windows today, including the most recent Windows 10 and Windows 11, as well as the server versions. When it comes to Windows programming, there are some key concepts that set it apart. Let's break down 4 distinct aspects that will be crucial for our reverse engineering journey. First, there is a divide between the kernel space and the user space. The kernel space is the inner sanctum of the operating system, where core components like the kernel and drivers live. The user space, on the other hand, is where your everyday applications run. Next is the Windows API, or Win API, which is the interface that lets software talk to the operating system. Then there are Windows handles, which are like opaque identifiers that let the system manage memory and other resources of a computer without exposing the underlying implementation. And finally, we've got the Component Object Model, or COM, which is a technology that lets software components communicate with each other in a language-agnostic way. Understanding these concepts will give you a solid foundation for digging into Windows applications. The Portable Executable file format, or PE for short. This is the file format that Windows uses for executables, DLLs, and some other binary files. A portable executable file is made up of several components, including a 64-byte DOS header, a DOS stub program, the PE header, a section table, and the actual program sections containing code, data, and resources. The portable executable file format was first introduced in Windows NT 3.1 and has been widely adopted across various Windows versions, including 32-bit and 64-bit systems, as well as UEFI environments. Understanding the PE format is crucial for reverse engineering a Windows application, as it will allow us to dissect and analyze the inner workings of these binaries and the resources embedded in them. The Windows loader is a crucial part of the operating system that gets our executables up and running. When we call create process or a related API function, the loader springs into action. Its key jobs include loading PE files into memory, allocating space for code, data, and other sections. But that's not all. It also resolves dependencies between DLLs and executables, making sure everything is properly linked. Then, it performs relocations, adjusting addresses in the code to match where the executable is loaded in memory. Finally, it initializes the executable, setting up the stack and heap. Think of the loader as the behind-the-scene magic that initializes everything for a Windows application to start its execution on a computer. Let's dive into how Windows manages memory. The operating system uses a virtual memory model where each process gets its own virtual address space. Think of this as a private sandbox for each process, keeping them isolated from each other. Within this virtual address space, we've got two main regions, user mode and kernel mode. Windows uses paging to manage memory, breaking physical memory into fixed-size blocks called pages. Page tables are used to map virtual addresses to physical addresses, keeping track of where everything lives in memory. And then there's the working set, which is the set of pages in physical memory that a process is actively using. Understanding how Windows manages memory was very important in the old days when computers had relatively little available memory and when the system actively used pagefile to support the needs of running applications. Let's dig deeper into how Windows uses paging to manage memory. The idea is simple. Both physical memory and the virtual address space is divided into fixed-size blocks called pages, typically 4 kilobytes in size. Page tables are then used to map these virtual pages to physical pages, allowing multiple virtual addresses to point to the same physical location in memory. But how does it work? There is a hierarchy. A page directory points to page tables, and those page tables contain mapping from virtual pages to physical pages. Each entry in the page table, known as a page table entry or PTE, contains important information about the page, like its physical address and access rates. This paging system allows Windows to use memory efficiently and provide crucial memory protection, preventing one process from snooping on another's memory. It's a fundamental aspect of how Windows keeps things running smoothly and securely. When it comes to interacting with Windows, APIs are the way to go. Let's break down the different types of APIs available. There is a Win32 API, which gives us access to core Windows functionality like Windows messaging and file input-output. Then there is the Windows kernel API, which provides low-level access to system functionality like process and thread management. If you are working with multimedia, there are APIs for that too, covering things like audio and video playback, imaging, and printing. System Services APIs cover important areas like user identity and power management. And finally, there are various other APIs available for miscellaneous tasks and activities. Understanding these APIs is key to building Windows applications and, of course, reverse engineering them. Let's see the Windows API in action. This C program is a simple Hello World example that uses the Win32 API to display a message box. As you can see, the code calls the message box function, which is a part of the Win32 API, to show the familiar Hello World message. And here is the result, a Windows message box popping up with our message. This is a native Windows application built using the Win32 API, which gives us a glimpse into how Windows apps are built from the ground up. And with such understanding, they can be reverse engineered as well. So what you can expect from this course? We will be diving into a range of C programming examples, using them as a foundation to explore reverse engineering techniques with Ghidra. By deconstructing and analyzing these programs, you will gain hands-on experience with Ghidra's decompilation output and learn how to correlate it with the original C code. The goal is to equip you with the skills to proficiently reverse engineer complex software systems. And to support your learning journey, all the course materials are available on GitHub. You will be able to follow along, experiment, and deepen your understanding of reverse engineering with Ghidra by the end of the course. If you are looking to dive deeper into software reverse engineering, I'd like to recommend my book, Software Reverse Engineering: Navigating x86 Windows Applications with Ghidra. This course draws heavily from the book's content. However, the book itself contains many more examples and insights that can help developing your reverse engineering skills. The book is available in both print and digital Kindle versions on Amazon, making it easy to access and read wherever you are. Additionally, the book covers subjects not discussed in this course, such as reverse engineering of C++ programs, classes, virtual functions, and more. I encourage you to check it out. Thank you so much for watching and learning with me today. If you found this video helpful, please hit that like button and subscribe for more content like this. Your support means a lot to me. If you have any questions or topic you'd like to discuss, leave a comment below or shoot me an email. I'm happy to chat. If you'd like to support me and the channel financially, you can do so through Ko-fi or Patreon. Links are in the description below. Thanks again for watching, and I will see you in the next video.